And now today's webinar series is actually our second webinar series in which will be related to the application of machine learning approach in seismic interpretation process. And now briefly about machine learning. So when we speak about machine learning, it normally involves big data and data-driven, as well as supervised and non-supervised technique. And so the applications of the realm of machine learning in petroleum geoscience have progressively developed over the last few decades. And machine learning, it resolves two significant issues in seismic interpretation, in which the first is the big data problem of trying to interpret dozens and hundreds of volumes of data. And secondly, is the fact that humans cannot understand the relationship of more than 3 types of data all at once. And so seismic and well data quality are the secret recipe to this process. And so without the integration between different geoscience disciplines, petroleum and drilling engineers, the occurrence of dry and problematic holes will exist. Okay, now, so before I pass the floor to our speaker for him to explain to you more about this topic, allow me to share with you the background of our today's speaker. So, Associate Professor Dr. Muhammad Sadani is a seasoned geoscientist with unique blend of experience in the oil and gas industry and teaching at University Technology Petronas. He has vast and rich experiences in all aspects of geological sciences, techniques, and practices as it relates in the oil and gas reserve, which include reserves mapping, analysis, modeling, hydrocarbon characterization, as well as feasibility and complex field development planning, well planning and implementation, as well as technical oversight of E&P operations from the geological perspectives. Now, he is known as an expert in the reserve maturation, safe and optimal recovery of reserves, technical integrity in the operations, efficiency, productivity, and excellence in the geophysical as well as geological services. All right, so now without further ado, I'd like to invite Associate Professor Dr. Muhammad Sadani to deliver his talk on the machine learning application in seismic interpretation. So please welcome Dr.
Assalamu alaikum, Fatin. Thank you very much. Can you hear me, guys? Okay?
Yes, Doctor.
Yeah. Thank you, Fatin. Thank you very much. So, can we start with الفاتحة؟ بسم الله الرحمن الرحيم. So, Assalamu alaikum wa rahmatullahi wa barakatuh. Students, undergraduate, postgraduate, academic staff, lecturer, associate professor, professors, industry, and experts. So I'm very happy today, by the way. Yeah, I'm truly incredibly honored to be invited to be a part of this webinar. Yeah. After 20 years of living in Malaysia, this is the first time joining you in this this community Geological Society of Malaysia, which is I'm very happy to be with Geological Society of Malaysia, because I believe Geological Society of Malaysia, of any country, this is the womb of all the geoscientists here. And happy also today that we have my close friends, so many people here, and the Mr. Sami Kurdi is here also. Mr. Sami Kurdi, 40 or more than 40 years experience in exploration, development, geophysics, sequence stratigraphy, geostatistics, and he is now expert consultant in machine learning. And he is also, a field supervisor of a couple of my students, one PhD and one master. Yeah. Thank you, Mr. Sami, that you are coming here. And also we have Mr. Ismail, my students, my PhD students. He will present something also in a few minutes, one case of application of machine learning in seismic interpretation. Yeah. So without ado, let us start. I would like to share my screen. Before I share, guys, maybe when I share, I cannot see your chatting. Yeah, because it will be in the display. I cannot see you. So please, if you have any question, you have to unmute and ask here, because I cannot see your chatting. Please, yeah. Okay, let me share. بسم الله الرحمن الرحيم. بسم الله الرحمن الرحيم. Okay.
You are muted. We cannot hear you now.
Oh, yeah. Sorry. Okay, can you hear me now? Can you see my slide?
Yeah, we can.
Yes.
Good, great. Yeah. This display is okay with you or not? What you can see now in the display? Only one slide, right?
No, we can see also your next slide and the notes.
Notes and next slide. Oh, yeah. You're right. You are right. Absolutely right. Absolutely right. Yeah. Wait. You are absolutely right. Yeah. Yes. Let me share it again. Share again. This one. What's about now? It's okay?
Yeah, that's better.
Okay, good. So رب اشرح لي صدري ويسر لي امري واحلل عقدة من لساني يفقهوا قولي. So this topic is machine learning application in seismic interpretation, and I would like to also to add pitfalls and limitations. Because any scientific method have its pitfalls and also limitations here. But the topic machine learning application in seismic interpretation. So we have to go through seismic interpretation first here. We have to understand a little bit about seismic interpretation here. We need to spend some time in seismic interpretation. I would like to start this one. As you know, we have four kinds of people in this world: those who make these things happen, those watch things happen, those who wonder what happened here, those who don't know that anything happened here. So someone say, I know from a very early age that I wanted to be first on this list here. This is Mary Kay. She passed away in November 2001, and she is a business woman in the States. And when she passed away, her personal fortune was 98 million US dollars. Same time also, if we go here, you know, we cannot solve the problems by using the same kind of thinking we used when we created them. We will see this one here. This one by Einstein here. So again, so this talk covers the seismic data interpretation, machine learning, definitions and applications, pitfalls and limitations. It's same time, but all this one in nutshell. Of course, yeah. Small nutshell. Touch and go. So again, there is some people say that we have four types of men or human in this world. We can say that a man that knows, a man or woman, yeah, of course, a man that knows and knows that he knows. These the scholars, ulama, as follow them or follow him. So a man that knows and doesn't know that he knows. He is asleep. So awaken him. It's like me. You know, sometimes I know, but I don't know that I know. Sometimes, yeah, sometimes, yeah. The third one is also, again, a man that doesn't know, and he knows that he doesn't know, as a student. And also, most of us, like me also, I don't know, and I know that I don't know. This is why I need somebody to teach me or guide me. The fourth type we have to avoid, and I hope that the man that doesn't know and doesn't know that he doesn't know. So it's a problem, or acting that he knows. It would be a big problem, especially if your boss is one of these guys. But I didn't see any boss during my 30 years experience, one like that yet. So now let us start in a helicopter view about this topic here. Why seismic interpretation and why machine learning? Because at the end, in industry, if we are industry, we have upstream and downstream. And you know that we need to find oil and gas. This is in exploration, yeah. So which block, which region, which basin, and how to get it. I know the where in details are reserves, facilities, this the development. And from the ground to the refinery, this is the production. This from industry point of view. Of course, from a research point of view is different, but it helps the industry. So the industry and the research should work together. The research cannot be developed without funding from the people here. If we have students and money, we can do research and also a good environment here. But I'm focused here in business. So we need to drill a well wisely. At the end, we need to drill a well. So because the well is very expensive, yeah. Some wells, by the way, more than 250 million US. Yeah, if you go to Google, something like that. Well placement and well path can be critical success. So how can we determine before or where to drill and predict what we will find before we start drilling? This is the issue. This is why we need you guys, yeah. And we still need you. Don't listen to the people, yeah. Still oil and gas still until maybe 2060. Who knows? We don't know. Don't worry about that, It's still number one from resource point of view. So this leads to the need for geologists, geophysicists, and other specialists focused on giving us images of the subsurface, and then interpreting those images in terms of geology and the fluids. So these the forecasting, these long time, by the way, yeah. But now this is not updated. But I think now it's extended to 2060 even, yeah. So we have gap, as you see here. We have gap because these the exciting production, these existing production here, yeah, and the production here from the existing the fields. So we need to recover this production to find a new place. Still, until now, some basins still not mature enough from research and the drilling point of view. So to fill this gap, we need G&G. So what we need to drill a good wells, one that we have low risk, maximize the rate of return. Wells can be very expensive, of course. The position of the wells is very critical. And we need an accurate understanding of the subsurface, of course, yeah. So the question now, how do we obtain an accurate understanding of the subsurface? The seismic now until now is the best tool in subsurface. Fill in between wells, well data. So until now is the best tool. And of course, why? Because it's so many research on seismic, and they pay a lot of money to enhance the seismic. Once we can enhance the seismic for resolution point of view, and for positioning and the focusing and the imaging point of view, we can drill good wells and build a very good geological model. So of course, the seismic cannot work alone. It should be with well data together, well data and seismic data. So I'm talking about focus and reflection seismic here. The refraction seismic is different. This one for near surface. Sometimes also use it in industry for in processing here. So the seismic data help us to evaluate new ventures, identify leads, plan and initiate development plan, FDPs, maximize production, monitoring the HCO, the hydrocarbons, the 4D. So seismic technology is critical for filling the gap between existing production and what we need to produce to meet future demand. So as you know, that is a seismic, the workflow. Normally we acquire seismic, process seismic, interpret seismic data, analyze key interval, business decision at the end. So what is that? The most important to remind you that every process of this one have its own uncertainty and so many assumptions there. Yeah. So we have to aware that so many assumptions here. We have to use assumptions. Of course, we have to use assumptions here. The Earth is heterogeneous. There is no, it's isotropic. The layer is horizontal. But the subsurface is not like that. Very, very complicated here. So every step of this one have its own risk and uncertainty. Or uncertainty. We can say uncertainty here. Why I'm saying that? Because at the end, we need this, the product of this one, to be input into machine learning. So we have to understand our input to machine learning to the machine before we put it here. To be aware by all the environment, technical environment of this topics or this process. So let us start by this one. Yeah, I will listen to this one, guys. Here, please, if you cannot listen, if you cannot hear the voice, let me know. Sound, the voice.
There are 4 basic operations in...
Can you hear?
Yeah, we can.
Yes.
Hello? Okay, good, great.
Structural seismic interpretation: picking,
to identify and follow the horizon to be mapped,
timing,
to measure the reflection time from datum to the picked reflection,
posting,
to transfer the measured reflection times to the map,
and contouring.
to show the structure, the relief, and we hope the closure of the chosen horizon.
Picking, timing, posting, and contouring.
From the section to the map.
So these at the end is like that. At the end, we pick timing, posting, and drilling. Looks easy. Yes, looks easy. Let us see. So now as you know, the well cost around the 20 to 100 million USD, while seismic about 4,000 square kilometer from 20 to 40 million USD. What's that? One well is, this coupled of, yes, a seismic survey is cheaper than to drill a well. This is why dry holes is, very, we have to avoid dry holes because a lot of money here. So now the seismic improved in the last decades, by the way, from 2D to 3D, wide azimuth, multi-azimuth, full azimuth, OBC for shear data, permanent reservoir monitoring 4D, cable under sensor technology, seismic sources, seismic processing, and you see here, if you see here, this one is one of the technology now in 4D. So why not, if we already have a plan when we acquire 3D, we have a plan to have another 3D or 4D to monitor the fluids. From now on, we have to design that. This is why they have an idea now to put these ocean bottom cable. They put that in the ocean bottom itself. The trench, they have a trench here, and they put it permanent. Just put the receivers there. It's not streamers now in the receivers, and then later, after 6 months, 1 year, just plug in, acquire, and record. So it save money and also keeps the repeatability, the positioning of the same, the positioning of the receiver in the same position, which is very, very important in 4D. So if we like here, if we look here, the single azimuth is wide azimuth here. Yeah. Big difference between them. Yeah. Big difference. Yeah. So this one is if we have an isotropy in the velocity laterally. So they acquire wide azimuth or multi-azimuth even. Yeah. And this one is 1996, and this one 2004 reprocessing data. Same data reprocessed. So what you mean? You will know that. You will know that these are same data. But if you like to look at the amplitudes here, is completely different than here. Yeah. frequency is completely different than here. Yes. So when you do extraction of attributes in this data, will be different than this one. Same data, but reprocess. Data changed, data driven, data and the interpretation. Once you change the data, your interpretation will be changed. It's a function. It's a function, because most of the people say machine learning is data driven. Any interpretation data driven. When you go to the field and to collect samples and you go to the lab, data driven. Because data, but the machine learning data driven, but big data. So now they know from 2D, 3D, the wide azimuth, multi azimuth, full azimuth, OBS, seismic resolution also enhanced here. Yeah, from this one from 1960 to now until now. You see here that because the geology also it's very complex here. It's not now the geology is complex all the time, but now the giant fields already gone. So we have to focus on the thin reservoirs and very complicated structures to find oil and gas. So this one just to show you the display, how now the 3D can help us in the workstation to display in any different ways, to look at the data from 3D, because the world is 3D. We need the 3D because the world is 3D. So this one also a 4D. I'll just give you something, to be ready. When you are these appetiters, you are ready now. When you have the main dish, you are ready now. You will be ready. So this is a 4D as example. The 4D also is monitor the fluids, and most likely this one recommended by the petroleum engineering, not from G&G. This one is normally also when we have the second recovery, where we like to drill a well to inject waters, where we need to inject water to push the fluid or to push the contact up. So we need 4D. So seismic interpretation meets the challenges face to face now. Face to face, just very quickly we will see some structures, whatever, we'll see. Yeah. So because this one at the end also there is the input for machine learning. So this is a surface. Oh, outcrops. Yes, outcrops. This is the reality and scale. Look at the reality. This is a fault here. Yeah. This fault, this guy, what meter as example, how big the fault? 2 meters, 3 meters, 4 meters, 10 meters. What is the offset here? Yeah. And what's happening in this one? Because fault is very important in subsurface. Can be conduit, can be seal, or can be both. Can be both also. Yeah. What is that? Look at this scale here. Yeah. Small faults. Ooh, very good, beautiful. I can touch the rock. I can, smell even the rock. I can have samples. I can use my 5 senses in outcrops in the field. So the field is very, very important in you because it should be in your mindset. Train your eyes from surface, because when you come to subsurface, you can use what you see in surface in subsurface to convince the others. But it's not easy like that. There's something there. Yeah. Look at this one. Oh, small faults, relay ramp here, beautiful. And look at this one. The fault is what is not is irregular here. Yeah. What is that? Look. Oops. Small, very small. Very, very small. So if you are familiar with something called fractal geometry, the world is like that. What you can see small, you can see in big also. Yeah. Same. But look at the complexity here, the complex. If you are now interested to produce oil, the behavior of production is not as you propose in your model, because a lot of things you cannot see. A matter of scaling and resolution. Now, what is that? It's a fault. What? It's one fault here. This is called the mechanical stratigraphy. The stratigraphy is different here. The rheology is different. Brittle, ductile. This from the Gulf of Suez here. I believe, guys, yeah, if you have seismic interpretation and you put a fault like that, maybe they will fire you or they send a warning letter. Yeah. But if they do that, show them that in reality we have a fault like that, because we are always afraid after 30 years, 25 years of them in seismic interpretation. You know, I see a lot of people, when you do the fault, when you interpret the fault in seismic, what's that? They don't believe it yet. You have to believe, you have to show them a real example case like that, or a model. Still very complicated here. What is that? Even if you try to analyze descriptive analysis, dynamic analysis, or kinematic analysis, structural geology, not easy. Not easy at all, yeah. Kinematic analysis, by the way, kinematic analysis is called, kinematic is cinematic, cinema. Kinematic, cinema, cinematic. Cinema is movie. Kinematic is the movement of the block. So, beautifully, I can see every layer here, yeah. Very good, yeah. But, remember, this one, in seismic, it will be like that. What? Yes. Forget about resolution now, yeah. You cannot get it. One loop can represent 20 meters, can represent 30 meters, can represent 10 meters based on the frequency and based on the velocity. So in seismic, we miss all these details, which is very important for us in subsurface and also the research. So keep your mind in that. Remember, please, yeah, different resolution from outcrop to well data, core, log to seismic. Be ready for that. So these are 2D seismic section. We have reflection here, the beautiful 2D seismic section and paper sections. We use this one by pencil color to interpret, but we don't know which is which. We have now peak troughs, look, the white and black. It's okay. I can interpret it, yeah. I can follow the reflector. But at the end, if somebody asking me, I follow the reflector, map the reflector, I have a map, two-way time map, that's two-way time map, yeah. So if somebody asks you, what is this map? Represent what? Top sand, top shale, top limestone, base what? What is that? So I have to tie something called seismic will tie. Seismic will tie is a first step to go from a G and G link, from geology to seismic. We have to tie this one. So it's another topic, by the way. But we have to create something called seismic will tie or synthetic seismogram. It's a 1D model. 1D model, because we know the seismic. Seismic is what? Seismic is reflection, AI, of course, AI differences, reflection coefficient, convolved with wavelet, plus noise. These are the noise is always there. So we tie, we have something called the synthetic seismogram. We know where we pick the horizon and interpret. Pick the horizon also, of course, yeah. Peak, trough, the polarity is another issue, yeah. So, okay, let us go one by one now. One by one now. Synthetic seismogram, it's also have limitations. So many also assumptions there. The wavelet, the frequency of the wavelet, the amplitude of the wavelet you use it in the shallow part is different in the deeper part. Which wavelet you use? Yeah. So many also uncertainty there. So keep it in mind, by the way. So everything, if every step have its own uncertainty and limitations, but we leave it at the end. We have to pick, map, drill. So this one, after we shift, you know, where we know, now we can know now what is this one. Before that, I don't know. Now I know what is this one. How? Because I can know here from geology. I have the logs here. Yeah. This reflector, I can know now. The geology give me formation tops, or give me this top, this gamma ray, whatever, this top sand, base sand, top limestone, base limestone. How to tie between the well and the seismic response through synthetic seismogram. Okay, good, great. Then we interpret something called, you know, auto tracking, something called, you know, manual interpretation. This one show you something called auto tracking. Auto tracking, just pick seed points, finish. The map is finished in minutes. Before that, in the early 1980s, we spent long time to interpret one horizon here, to a reflector. It can be 1 week, 2 weeks, 3 weeks here. But now by click. But again, when you click, you have to, when you create a surface, you have to QC. You have to QC because so many misties there. Yeah. So you are also very important. Your decision, we need your decision. Every step in seismic interpretation need you, not machine. Don't say this is the machine product. No, it's your product. Now it is for your responsibility now. When you come to your boss, your review, you have to edit it and review it. So this one also geomorphology now. So we can get a lot from Seismic. Yeah. This one also unconformity, sequences, phases. We can go, and this called seismic anatomy. This also just I show you, train your eyes about the data and your objective. What's your objective? You have to understand your objective is what. The objective structural geology, phases, attributes. Based on your objective, you design your workflow. Yeah. So in this one is WDDM, this West Delta Deep Marine. You see here we have stacked channels here. It's not easy, complicated here. This is a produced field, by the way, in Egypt, in Delta. So we have 2 stacked channels on top of each other here. You see is the bright spots here. Yeah? Remember this one. When we go to the machine learning, this one, if I ask this one need manual interpretation or auto tracking? Of course, manual. Auto tracking will be failed here. Yeah. So we have to use it manual here. Yeah. Manual interpretation, it needs experience. It needs experience. You have to decide where you go, up or down. It's your decision based on your experience and your data, of course. So we have also something like pull up. We have a channel here. Yeah. This channel filled by something. We have here, if you look here, we have a little bit high. This high is why this high, someone says fold. But this fold, why this fold is under this channel here? Is related to something in the channel itself. Maybe we have in the channel sediments with high velocity, which make pull up the reflections below the anomaly. So this one is not real. This one in time domain only. So we have to solve this one in depth. If you pick this horizon here and interpret, you have anticline, drill. No, failure, because this one is not anticline. It's just the illusion due to velocity anomaly. We have also like that. What is that? This is good. We have 2 channels here, channel here, and there may be gas chimney. Good, drill. We have here channel here and channel here to have 2 reservoirs and the 2 reserves. Good, go ahead, drill. Yeah, but wait a minute. In 3D, it's a meander channel, but you cut the channel into 2 times, one here, one there. So if you drill a well here, the pressure regime will be connected with this one. This one could be 1 reservoir. So when you claim your reserve, you have to claim it as 1 reservoir, unless you have barriers here. Yeah. Barriers, it means this reservoir is not connected and pressure connected, so we can find the 2 fluid contacts. But if it's connected, we have to have 1 fluid contact. This is how the 3D help you. So also attributes here. We have something here in attributes here. Amplitude extraction, DHI, called direct hydrocarbon indicators. If you look here, this bright amplitudes here fit with the structure closure. Great structure closure, and they supported by amplitude drill. Good. But if we look here, we have structure closure here. But this anomaly is outside. So don't drill. No. Wait a minute, please. Do some work here. Who knows? Maybe this one is stratigraphic play. Is not structure play here. This one we can get it from seismic. I am just to be ready. Yeah. So now we coming now to the world of fault interpretation. We have faults here, very beautiful faults. Okay, good. Interpret. Good. These are fault. Finish. No. Please let it put it up a little bit. Finish. No. Please let it put down a little bit. So it's up to you also where you finish your fault terminations in space, in depth, and in space also, in laterally. So again, these are fault here. We are lucky here to see the fault plane itself, the fault reflection. Good, great. Go interpret. These now reflection from fault planes. Great, these are fault here. Yeah. Okay, good. Little bit need to be up. Good. We have also discontinuity here. Yeah. Put a fault. Yes, good, great. But this fault not connected? Yes, right. It's up to you now. Lead a decision. Connect the fault or not. in section on in space, it's your decision, and you have to defend your decision, because here, connected or not connected, it affects a lot of things when we drill. We'll see examples from this one. So good, great, okay, good, very good, very beautiful fault. We have this continuity. Interpret, breaks, strata reflection. Join them up. Continuous high reflection. Okay, so we can get also so many information here. We have higher frequency here, low frequency here. The phases changes also. We can get a lot. We can write a paper on just write, the paper, not write a paper for publication. Write a paper on this section only, based on the reflection amplitudes and based on the structure also, So interpret the fault. Good. What? Mistie. Yeah. Mistie. Why? This reflector is not a reflector, Why? Because in this section, maybe you have sand, shale. Very easy to have sand and shale against each other, but this sand is not this sand. This shale is not this shale, It happens, We have mistie here. We correct the mistie. It is a world of interpretation. Now, systematic offset platform. Continuous reflector, surface, good, great. So, let us focus on this one. If we focus this one, is not a straightforward. So can we do that? Oops, relay. The fault stop here and stop here, This one accepted, So we have now, continuous surface or relays, Now a fault, one fault, or couple of faults. Oops, what is that? All of that is interpretation. It's your decision, You have to defend it, Single continuous fault or small faults like that. Both scenarios can be happened, and both scenarios have its own different impact at the end in your calculation of reserve, whatever. If this fault is, a bounded fault of a closure or field, very, very important. So now, this is the expression of faults here. Okay, good. We have fault here also. Beautiful one. So what we can interpret it like that. Yes, this is a rift. Still rift package, post rift, pre-rift. This one, we can use it also in machine learning. Yes, we will see. It means that I can define some packages. If I define these packages, it can help me to predict in the other lines these packages through machine learning. Yes, we can do. Wait. So we have also thrust like that. These interpretation. Someone say, this one is not yet. Okay, go ahead. No problem, by the way. No problem. If you interpret by different interpretation, it's okay. But you have to defend it. It should be logic. You have to defend it. It's like that. Simple. Also, two thrusts here. Can be like that. If you like to change the interpretation, it's up to you. No problem. Based on your experience. But again, explain, defend. So what is that? A beautiful, reflection. What is it? Beautiful reflection? It is what? Yes, it's a contact here. It's a contact. So why this one is here? We know that the reflection comes from different layers. No. Reflection comes if we have different AI. Whatever different AI. If you have different AI from rocks, from fluids, it can give you reflection. So these, these are variations, of which change laterally or vertically. Most likely the vertical change is more than lateral change. So not every reflection is strata. So we use also the time slices to define faults. If you look to this data I worked in this field, by the way, this field from Saba. If you look here, we have to interpret it. We have to, and you observe something here. Interesting feature. This feature here. This feature is flat here. Something like contact. But what is that? And we asked it, I was asked to interpret this one and they give it to the modeler. At the end, what I have to do? Interpret. But this data here, how I can do it here? No problem here. You see here, just draw a polygon here, and this one is uncertainty, big uncertainty. But we have to fill the gaps. Fill the gaps based on modeling experience. We don't see the reflection, but try to guess where is the reflection. Why? You have to do it because the data is like that. Don't say I cannot do it. Do it. Do the best and say these are my model. These we have big uncertainty here. It's okay. These produce field, by the way. So these gas whipped out the gas. What is that? Forget about it, yeah. Nothing. There is no correlation here, no reflection here yet. It's seismic data. Also, we can also define on lab, down lab, the sequence stratigraphy. Also, we can define here, the reflection determinations, and this one from seismic give you all ideas here. Also, sequences here, yeah. Good, great. So this one of the big problem, by the way, yeah, we faced when the faults could intersect each other, the fault terminate in each other, because if the fault close to each other, create prospect. If the fault is open, no need to, we cannot drill, yeah. So here we use very, very intensive, arbitrary seismic section to be sure that this fault is connected or not. Is still a problem until now. We solve it. How we solve it? We solve it by seismic attributes, by modeling, and the experience here. This fault shouldn't die here. It should die later, based on the fault throw profile, the structural geology analysis here. So it's very, very important point here. Until now, it can be solved by machine learning. We'll see. Who knows? We don't know. I don't know. So we use this one here. So why machine learning? Analyze the big data, determine relationship between different types of data, discover nonlinearities in solution, improve efficiency and accuracy over time. And because sometimes also I heard one of the guys when I was attend one of the course, the guy say that there is a relation between in the States when they go to the beach here, there is a relation between the shark attack and ice cream. The people eat ice cream more and the shark attack more, yeah. Both of them more, yeah. But there is no relation because in summer the people go to the beach and they attack by shark more, and also they also eat ice cream. But there is a relation there, yeah. But this relation is nothing. So we have to think also, yeah. Machine learning can give you the hidden dimension or hidden relation which we cannot see or we cannot do it, yeah. So reveal geologic features, properties, or trend that are difficult to see or not seen at all in conventional approaches. Reduce risk. So this one is 2018 when Total, they do the lead at the time. Total and the Google Cloud here have signed an agreement to join development artificial intelligence AI solutions applied to subsurface data analysis for oil and gas. They ask the staff from Google Cloud to come to the Total office to sit together with the geoscientists to work together, transfer technology, transfer experience, and now they have a product now, by the way. Yeah. If you go to Google now, you will find now their product now. Beautiful work, yeah. And you look at how the company take the decision to lead early, not waiting until somebody do it and I will do it. It's not like that. So these the challenge and opportunity for machine learning in geoscience. So deeply grounded in physical laws, geoscience is like that. Physical laws, machine learning is data driven. There is no physics there. Yeah, is a matter of algorithms here. So the geoscience also feature have space and time relations, are highly multivariable, non-linear. Our geological and geophysical data employed to interpret geology have challenges of multiple resolution. And you have to know, guys, yeah, seismic data is non-unique solution. Non-unique solution, yeah. Example, if you have 16, it can be 2 times 8, can be 4 times 4, can be 8 times 2. Different than 2, but is non-unique solution, yeah. So these, the machine learning by definition, these by Arthur Samuel, 1959, field of study that gives the computers the ability to learn without being explicitly programmed. But Tom Mitchell in 1998 will post-learning problem. A computer is said to learn from experience E with respect to some task T and some performance on T as measured by B improves by what is that? The definition itself need a machine learning to understand here. Wait a minute here. Here, what is machine learning? Suppose you interpret, recognize, or identify a channel on seismic line. Mark it as a channel. Okay, we know that. And based on that, learn how to better filter channels. What task T in this setting? Okay, classifying the seismic as channel or not channel. This is what? This is a task. Watching you label the seismic as channel or not channel. This is the experience. Need experience when to label. Yeah. The number of seismic lines, data volume correctly classified, channel, not channel. This is the performance. So machine learning or AI is fall between statistics and computer science. It used all of them in the core. So there is a big overlap area between AI, computer science, and the statistics. Yeah. It's not easy to separate between them. So it's also, you know, the machine learning is under AI, is part of the AI. And the under machine learning, we have deep learning here. So we have also something called supervised classification and unsupervised classification. Okay, these two types of machine learning methods used in seismic interpretation here. Okay, unsupervised classification and supervised classification and unsupervised. And we will see also the clustering here. Clustering, we'll see later clustering. Okay, good, great. So we have machine learning here, supervised learning, unsupervised learning. Supervised, we have classification and regression. These are big terms here. And we have something called clustering. Here, supervised, here, unsupervised. The difference between them, the supervised versus unsupervised. Supervised should be labeled data, direct feedback, predict output. Unsupervised in non-labeled data, no tables, no feedback, find the hidden structure in data. This is a big difference between the supervised and unsupervised. And as you will see, the unsupervised, it needs a high experience. At the end, you need to interpret. The computer will not interpret for you. The computer can put horizon faults, but at the end, you have to interpret it. You have to say it's logic or not. So these machine learning, and you know, the in seismic interpretation, we use computer algorithms. Machine learning is useful in seismic interpretation because it solves two significant problems: interpreting images, large volumes of data, and understanding the relationship of various types of data at once. So we have two types: supervised classification and supervised. Supervised, the correct or desired answer is known. I know already the answer. Based on the training data, I know the answer. So I train the computer to know the answer every time until I already okay. Then we have to test the program to something is not labeled. So we will see a very easy example here. So now the has known results, and then the training data set is applied to another data set with unknown results in order to predict. Prediction. We are working as predictologists here. Prediction here. Predict its output. Optimally, the learning algorithm will be able to determine class labels. Example of supervised learning, we have something called MLB, we have some probabilistic neural network, we have the random forest, we have the vector support vector machine, SVM. These name of algorithms or name of models under the supervised learning. So unsupervised learning, we don't know. We are looking for the pattern. We don't know the answer, but we need to see the pattern here. What is pattern is very, very important in geology. Geology, so many patterns in geology. So many patterns in geology. Discontinuity, you know, channels, you know, the bars is features there. So example of unsupervised algorithm is like PCA or k-mean clustering or SOM. So these just to give you an idea about the regression and the classification of the supervised, the linear regression, logistic regression, decision tree, gradient posting, and all this here. So these very simple, you know, to show the difference between here gene 1, gene 2, surviving here, the years, and this one is very easy here, regression line here. But this one clustering here. This clustering, we cluster here. This disease here, healthy people here, is two clusters, healthy and affected. So now, guys, if we ask now here, can we predict what is this one in this one here? Can we predict it? Can we predict it quickly? What is the number here? Oh, I know the number. How? This one is 25. Great. Now, congratulations, you have successfully accomplished supervised learning. Supervised learning like that. Input data, answer, input data answer. From this one, I realize this one is the the square. So 5, it will be 25. Simple. Supervised learning. So this one also give you the original clusters here, data and clusters, and here after clusters here, the unsupervised learning. So it's like that, the biological neural network, we try to do it like the neural network, which is impossible, of course. It's impossible, yeah. But we try to mimic our neural. Give me, please, yeah. I need time, please. So the neural network here, a mathematical abstraction of biological learning process that is applied in the computer. This is the neural network now, okay, which can be applied in supervised or unsupervised. We have input, we have layers. One layer is called neural network. More than one layer, we can deep neural network. If we use images, we call it convolutional neural network, CNN. Neurons learn by either minimizing incorrect answers, which is supervised learning, or by adapting to the characteristic of the data. This is unsupervised, like that. So now this give you an idea about supervised here. As example, this one, we have features here, RMS, amplitude, envelope. This feature called feature, this one, seismic attributes. The seismic attributes. And we have so many seismic attributes as example here, and we enable here the classes, and then we predict this known output. If the system is okay, the prediction is okay, the accuracy is okay, then I will go to test the model. So this one is the one which we use the training here. These are small data set. We have a case for this one. And also this one is like that, the labeled output, we create model back. Now, after we do this one, the training and everything, we create model. Once we create model, we can apply model to new data from the same data, yeah. New data, from the same side, whatever this data, logs or whatever, yeah, unknown. Then it gives you here, the how many classes. These are neural network here. These are deep neural network, more than one layer. Okay, or convolutional neural network, which is most popular now. Deep learning approaches, CNN. They use it for images. So now we have, a case study. This case study by Azimuth. Mr. Sami is here. This case one supervised regression here. So here we try to do what? We have sonic logs. We have existing wells. Yeah, and we have seismic data. So we in this seismic wells, in these wells we have sonic as example, sonic logs. So can we create pseudosonic in every single trace of seismic? How we can do that? Machine learning. We have well data, logs, and we have seismic data. If we can somehow to do seismic attributes, and put the label here, and they try to train the model, that this one at the end, there is the value of the sonic log. So by this one, we can create in every single seismic trace a pseudo-sonic, pseudo-gamma ray, pseudo-density. Here in this case, pseudo-sonic, which it means that sonic is slowness. Sonic is slowness, which is 1 over velocity. So once we have a sonic cube, this one is the difference between traditional depth conversion and the machine learned depth conversion. This one for depth conversion. So the traditional one, we have to have horizon, the distribution dependent on well spacing, vertical range, and also horizon dependent. Velocity model mainly focus on depth conversion, high uncertainty. But when we go to the machine learning one, is horizon independent. No need for horizon here. Vertical range is that of seismic data. Velocity model can be used in a QI also. Yeah. So when we have a velocity cube from well data and the machine learning, not velocity cube from seismic. Forget about it here. We are talking now about velocity cube I'm not talking about now pre-stack depth conversion or sorry, the pre-stack depth images. No, or depth the data itself. No. So I'm talking now about the how to create a velocity cube from well data and seismic. Robust, more robust, yeah, by machine learning, yeah. And in the same time also, when we build the model, we can give you uncertainty, and it can be interpreted, can be used for processing, can be used for fully. It's ready for any purpose. And also it was produced as SIG-Y. So this is a workflow, by the way. This is a workflow of the machine learning seismic to well log prediction and the depth conversion. We have the well log here. We extract attributes. These amplitude in SIG-Y here. This one in SIG-Y, and we do here the build DT model, the DT delta T model, machine learning model. Build here the machine learning to model to predict any log here. Just put it here, by the way. Any log can do it, yeah. Gamma ray, whatever, yeah. Same workflow. At the end, we'll have a depth converted SIG-Y or velocity. You can use it for any to convert the seismic in time to depth. Not only this one, by the way. We can also, this one is a product, by the way. This is a machine learning, delta T. This is a delta T. The Z here is delta T. Amplitude, but we have delta T here, yeah. This is by Azimuth Geosolution, Mr. Samuel Cordia. And also at the same time, this is depth, time and depth. You see the time here, and we convert this one into depth by this model. Not only this one, but also we can create probabilities. Once we have the data, we can create probabilities. We have a standard deviation, whatever 1 or 2% around it. We can predict also. We can, generate P10, P50, P90, whatever. So the data is there. So machine learning, big data, and also producing big data also. Yeah. But here, how we can do that without machine learning? Yeah, it's a very good product here. So here also, this one is the P90, P12, P50, P90 probability cubes. Also, these probability average velocity, the average velocity volume. So you have different volumes of velocities here, which, by the way, accepted, because velocity is a big question in subsurface. Big question in subsurface velocity, always question. So this coming to this case, by the way, we have a very good case just published this year by Mr. Ismail. He's he's doing the PhD with me, and inshallah will be soon, Dr. Ismail, inshallah by the end of this year or early next year. Dr. Ismail, Mr. Ismail,
yes,
can you hear me?
Yeah,
Yeah. So I would like, by the way, I would like to invite Mr. Ismail just to show you how he do this very beautiful work in few minutes, Mr. Ismail. It's okay, Can?
Yeah, sure, we can.
Okay, guys, can you hear Mr. Ismail? Hello, Ismail, you can
Yes,
talk,
we
Ismail.
can.
Yeah. Okay, good. Go ahead, Ismail. Yeah. Okay.
Okay.
So Ismail, this is the title. Yeah. Go ahead. Yeah.
Yeah, thanks for the opportunity to show our work here in CSI. This is part of our machine learning and deep learning research in CSI. And this specific case study is focusing on evaluating principal component analysis to reduce seismic attribute dimensions. As we know that we have large amount of our available seismic attributes, and the aim of this study is to investigate how we can reduce the amount of seismic attributes, avoiding the redundant and irrelevant and meaningless attributes to produce a robust machine learning models for prediction. And this case study is applied on the one of the fluvial reservoirs in Malay basins, offshore Malaysia. So
Ismail,
can you add, Doctor, on this?
Because I would like to add here, by the way, this is the most important step in any, please guys, when you start in any project in subsurface, you have to start by a good correlation. Yeah, at the end you are a geologist here, so good correlation, because this one is the this one should be correct and agree. By the way, in the past we have to sign that this correlation is okay, because based on this correlation all your work is based on this one. This correlation, it means that this package is this package, this package is this package in the time, a stratigraphic frame, and this one which have a meaning here. So please, yeah, when you start any project in subsurface, do a correlation, review your correlation, and be sure that the correlation is okay. Then you can proceed. Okay, go, Mr. Ismail, go ahead.
Yeah. Actually, this is the workflow of this study. It's broadly subdivided into domain knowledge part and machine learning or conventional machine learning workflow. So the first part of this study actually is based on the seismic interpretation knowledge, geological and geophysical knowledge. And the ultimate goal here is to produce training data or labeled training data. So we do the traditional work by, as Dr. Muhammad mentioned at the beginning, to calibrate our seismic to geology. So we do well log correlation and log motif analysis to understand the stratigraphy of the interval. And then we extract seismic attributes. Actually, the attribute extraction is based on our knowledge, previous knowledge, and also the response of the local geology. So we extract or we have already extracted 31 seismic attributes for this case study, and then we reduce these 31 generated seismic attributes into principal component analysis, into principal components. As you know, principal component analysis is mainly used to reduce the data dimension. So in our case, instead of 30 attributes, we reduce the attribute dimensions into a couple of principal component.
Good.
And then we carry actually seismic geomorphology analysis.
Okay, good.
Just to identify the stratigraphic features, the fluvial depositional elements in this interval. Yeah. So the aim here is just to identify the different architectural elements of the fluvial system and label the classes or facies based on that with the help of the well logs. Then when we produce label data, we do the traditional machine learning workflow. We build machine learning models, test them, and apply them to predict the fluvial facies in the interval. So this is just to show the seismic response. We are computing different seismic attributes in the interval of interest.
Great.
In this example, we have envelope, RMS amplitude, GLCM attribute, and spectral attributes showing the response of the different features here. We see sand filled channels, we see point bars, we see delta lobes, crevices play, and so on. Okay. So next we use, can you move to the next? We use this attribute expression. Yeah. We use the attribute expression along with the available well data and also the vertical section. So in this slide, we are showing a composite seismic line passing through the 10 wells, the available 10 wells for this study. So we can see the seismic expression of the different features. As you can see here, we have the delta lobe, the point bar, crevices play. So we identify their expression in terms of seismic amplitude, and also we produce RGB color blend to interpret those depositional facies or fluvial depositional facies. The end product here is an architectural element map of the different depositional elements. So this is basically is intended to help on the labeling the data for machine learning model building. So next we come up with 3 classes. Actually, we combined all the depositional elements into 3 classes. So class 1 here is combining the sand-rich features, the sand channels, the point bars, the delta lobe, and so on. So the sand-rich features are combined in one class, which is class 1. Then we have the class 3 is the low amplitude response of the flood plane. So class 3 is basically the flood plane, and the mud filled channels, which are showing a very weak amplitude response. And in between we have the crevices play. So this is our input actually to the machine learning exercise.
Ismail, the squares here, yeah. Talk about the squares.
Yeah, the squares here is where we pick our labels or our training data. So those squares are posted on a horizon slice. So we extract 2,300 samples of each class to be represented in our training data.
So guys, we use this one here. Inside this one, we have data now. As example, as Mr. Ismail, 2,000 something samples. Every one has its own different Z values. So many Z values based on the attributes. If we have 20 attributes, 20 attributes values inside this square. This square is the training. We use this one for data itself. Then we will see now here. So please remember, this one is not image. It's still tabular data, right, Ismail?
Yes, it's tabular or point data.
Exactly right. Okay, good, great.
Yeah. So next, if you see the black table here, this is our training data. It's basically or generally divided into features or attributes and the desired or output class. Here, this table is showing different attribute values, and then each combination of attributes is labeled into different classes. So before using these features or this training data in the machine learning model building, we do some correlation analysis to avoid the redundant, the useless, or low correlated attributes. And then we select only the relevant or important attributes in building our machine learning model. The figure or the map to the right is correlation heat map. It's basically show the correlation relationships between the data, between the feature themselves, and also the desired class. Dark green here is indicating strong positive correlation. Dark brown is related to strong negative correlation. So what is our target here is to avoid the highly correlated attributes. So highly correlated attributes are redundant. They only increase the computational time and building complex models. So we try, if we have 2 or 3 or 5 highly correlated attributes, we can pick only one of them to represent those attributes in our model. On the other hand, we are also interested on the attributes that are highly correlated to the desired class. So the highly correlated attributes in this example, if you can see, envelope, RMS, and other attributes. So those attributes are very correlated to the class. So they are very important and significant in our machine learning model building. So we pick basically the highly correlated attributes to our desired class. So instead of 30 plus, we just pick a couple of attributes to train our models on them.
Great.
Yeah. So we train basically 3 algorithms or 3 machine learning models. We have the neural network, random forest, support vector machine, and we use different inputs. We use attributes and also we use principal component. And those figures are showing the performance metrics. We compute precision, recall, F1 score, and accuracy. So simply those numbers are indicating the accuracy or the performance of our machine learning models. If you look at the row, the column to the right, this is the accuracy of those models. All the models are showing excellent performance above 95%. So all those trend models are applied to predict our facies or desired class in the whole seismic volume. Those maps to the right, A and B, are a binary classification example showing channel versus non-channel facies. So basically the seismic volume is classified into two classes, the channel facies or the sandwich facies and the floodplain. The C and D actually is showing three classes classification scenario. We are classifying the data into sandwich channel, sandwich facies, floodplain, and also crevice display. So this is our end product, actually, our product of this classification. And then you as a geoscientist, you have to actually calibrate this product and take decision based on this. In this example, we are using different wells actually to calibrate this classification and make a decision based on that.
Thank you, Mr.
So
Ismail.
I think, yeah, that's all for this one.
That's great. Yeah, very good. Thank you, Ismail. Thank you very much.
Thank
And
you,
you know
sir.
and we know that the ANSI or this field is a very good data, by the way, very good seismic data. But we have to use the seismic quality is very important here. We cannot apply a new approach whatever in a very poor data. It's not fair. So we have to use it if it works in a good data. So we then use it in also other data. Good. These also these case number 2 supervised, and using here the different neural network here, random forest. This is case number 3 now. Now we go to the convolutional neural network, CNN. As example, CNN, it works in images here. Images here. It's like that, Go to the border first from layer to layer, from layer to layer, until this is the one which is famous in very dog, cat, whatever. They use a CNN, car, and all things around us. It's like that. They use the image here. So this paper is published in 2018, and very common, by the way. This one is the for automatic of seismic interpretation of the this is the guy Wilden, the Norwegian guy, for salt. Very common, by the way. Yeah. So layer 1, layer 2. At the end, this one just because convolutional neural network is layered. Yeah. Is layered. Sometimes it's start by big one and go small and back again to big one, and sometimes it finish at the end here. Yeah. So it's also back propagation, also back propagate the until the result, or until we know this is a cat. Yeah. So the error is very small. Let us see how we apply CNN in salt interpretation as example. If you look here to this one is training slice in line training. Yeah, this is a manual interpretation. These salt class, these two classes, by the way, salt, not salt. Salt is the red, not salt is the green. First, we interpret here. So it's beautiful, by the way. Yeah, it works like that. Interpret line or close line, and then predict the others. It works. So we have here two classes here, salt and non-salt. If you look here, manual interpretation and predicted. The predicted one is the red. The one which the interpreter do it is the blue. Here I need to stop here for a minute. A minute here, very, very important. I like this slide here and this paper. Why? Because the result now you are facing now the result of machine learning. Good. You have two options now here. To believe in your interpretation and say no machine learning, we have to modify the algorithm or the architecture to be okay with my interpretation, or forget my interpretation, I believe the machine learning one. Both cases need you. It's not your, this one is your experience now. You have to decide. You believe this one, the red one, or you believe the blue one. If you believe the blue one, you have to edit the model. If you believe the red one, you have to edit your interpretation here. So it's like that, simple like that. These are a very good example of this one. This another case history. This case number 4, whatever. This one to predict faults. Faults, yeah. So this one supervised fault link. This is the superimposed. Sorry, and you know this one is the. This one is you know, this one, by the way, by the authors here from Department of Computer Science. You know, and also the second one from electric and computer engineering. Yeah. So there is no geologist here. Yeah. The two authors here, or the three authors here, one of them is computer science. The others is from electrical and computer engineering. So they like that. So they create a workflow, calculate seismic attributes, extract features, then train CNN model. Then train CNN model and predict geologic faults by applying these CNN models. So now they also use here, you know, these maximum curvature. These maximum curvature is very good attribute for discontinuity. Not all discontinuity is false. We know that. And after that, they like the likelihood here, the green one here. Yeah. Good. Then they predict the faults. If you look here, this one, the red one is here. The black one is the training. The training, sorry, the supply training labels is the red one. But the black one is detected from the machine learning. It's good. It's good. Good results. Okay, good. Enjoy. Enjoy these faults. It's okay. Enjoy, yeah. And map it. And give it to the modeler. Please, if your modeler accepts your model, let me know the name of this modeler. Yeah, I need to see him. Yeah. Okay. So these also how to predict faults using CNN from data, from seismic data. If we look to the second or the last one, yeah, beautiful one, not last one, sorry. This one, this paper published in the Leading Edge 2018. And what happened here? Yeah, the title is very interesting. Yeah, machine learning and learning from machines. If you look here, guys, you will find that this one is 91% thin section. Thin section, yeah. The machine learning identified this guy here, 91% microphases. These are microphases are there. So this is the ratio between this guy face and this guy. So the machine learning said, these microphases, go ahead. Go ahead, what? But 86% human. Same time also, if we have a basin, you know, burial history of basin, the machine learning can identify it as depth model, velocity model. So here just that the guy here tried to show here image segmentation example, a misclassification of a human photo from a paper by this guy with limestone thin section. These very nice, you know, the results. Yeah, very nice results here. So now, if you go to this guy, if I ask you now, what we see now, how many patterns or clusters can we identify? We can say no problem. We can say, okay, based on shapes, it's like that. But based on fruits or non-fruits, it's like that. But based on the color, is like that. Great. Now, congratulations, yeah. You have successfully accomplished unsupervised learning here. Welcome to the, you know, the clustering, not classification here. So the pros and cons of the unsupervised learning neural network. We're still in neural network here. Unsupervised, clustering, not classification. We have very fast to start, difficult to measure, disruptive insight, require more experience, and the curse of dimensionality. What this one? This one coming from geophysical insight. I copied from geophysical insight. Dimensionality, and I think already Mr. Ismail talking with you about how we can reduce the dimensions, reduce the features, you know, because we have so many features, we have so many dimensions here. So there is a way to say that this one is like this one, no need for this. This one is like this one, no need for that. As example, a mandarin or orange, close, okay, no problem. No need for this. We can use the orange. Yeah. It's something like that. So it's called the PCA, Principal Component Analysis. This one is the most popular dimensionality reduction approach in unsupervised. But as you see, Mr. Ismail already presented, you know, his work. He used a PCA in supervised machine learning. So PCA, a linear mathematical technique to reduce large set of variables, like seismic attribute, to small set that still contain most of the variation of independent information in the large set. Beautiful idea. Still keep the differences there, yeah, but no need for all this here. By the way, same of also of attribute world. When we do seismic attributes, so many attributes close to each other. Semblance, curvature, and tracking. One of them is enough. It's also all of them give you discontinuity. So PCA helps find the most prominent and important seismic attributes. So now we have something called self-organizing map. SOM is not actually neural network, but it's something like that. It's as I know from Mr. Sami, you know, he's my guru in machine learning. So he said that this one it's used before even machine learning. Yeah, I think, yeah. Maybe he can explain more. But this one is not the SOM. Is like neural network also. At it's unsupervised. At the end, give you clusters. So how it works? Survey space, calculated seismic attributes, attribute space, and this attribute space will try to find the neurons here. Here 256 neurons or clusters. At the end, give you 256 clusters. And by these clusters here, you see here, every cluster has its own color. At the end, we can put this one into your survey. Now we have different clusters in this top reservoir, whatever. Then I can off and on any neurons of this one, off and on, like, you know, the opacity in seismic interpretation. So what you like to say? Let me explain to you here. Yeah. Now, this is a case history. Now we have a case history. This case history, we have, you know, this reservoir 3,900 feet reservoir up from fault, approximately, you know, 100 feet reservoir sand, 2 producing wells, A1, A2. Previously 7 wells drilled in area, all wells or wet or low saturation gas. So the goal, what DHI characteristics can be identified to refine reservoir interpretation and deploy in the region for further exploration. So what the SOM do? So we have 20 attributes. Input PCA, go to PCA, yeah, to reduce this one. Then what is that? This one is a very nice idea here. Yeah. This top reservoir amplitude, time structure, man, or depth, whatever. Yeah, this amplitude overlay. Yeah, it's very clear, by the way. The amplitude, you know, the confined by the structure. Very good. Yeah. But look at the machine learning SOM map. What is that? They on only the very low probability. Very low probability. Yeah, we have clusters. Yes, right. But these clusters have probability. Yes, right. Now, let us see the low probability cluster. Why? Because low probability is anomaly. Yes. If we have anomaly, it will be low probable. So then we can see that this low probability confined to the structure. It means that very good results. Very good results here, yeah. Of SOM. Great. So even now we can also see the SOM results in sections now. In sections, you know, we can also off and on to see the probability. Now we have two in this seismic section. We cannot see anything here, but here looks like we have two. You know, here this one undrilled the anomaly and not connected here with this one. Good idea, good results. It means that I can go to this one. It's unconnected here. Without machine learning here, it's very hard to do that. If I'm not mistaken, yeah, I believe that. So the summary and the conclusion, guys, I know you are very high. You know, the machine learning applied inside mechanism through, you know, the whatever horizon and fault picking, also geological bodies in identification and extraction, also seismic features and the stratigraphic boundaries interpretation. Guys, please, DDHI, please, yeah. My advice, number one, don't fall in love in your idea. Don't fall in love in your idea, in your model. Once you fall in love, you know, if you fall in love in a girl, even, yeah, you'll be blind, yeah, deaf. So you have to good observer. So if you fall in love in your idea, it means that you cannot hear, you cannot see the others, you cannot see that there is a data update. So please, yeah, be open-minded, yeah. You have to defend in your idea, of course. You spend time to create your model, defend it, yeah. But once you find something from your peer review, or when you show your work in conference, as example, conference is a very good, you know, environment, because conference is like a theater. If you are actor, the real challenge in the theater itself, because in the theater itself you are in face to face with your fans, with your audience. You see the reaction, but it's different than if you acted in a movie. These years later, when you publish, you know, paper in a published paper, yeah. So you have to have peer review. So don't fall in love in your idea. Number two, please, don't be clicologist. Tick. Be geologist. Don't be clicologist, be geologist, yeah. And be sure that the future now is still, we have so many jobs. But please, it will be, I think, will be better if you know machine learning than the others which you don't know machine learning. So now, learn from yesterday, live for today, hope for tomorrow. The important thing is what? Is not to stop questioning. Again, this one from Albert Einstein. Thank you very much, guys, and really sorry for your time. Thank you very much. I know this. I know. Thank you very much, guys, and welcome to any Q&A session. But I'm very happy that we have Mr. Sami with us. Mr. Sami Kordi here, right? Mr. Sami, are you here?
Yes.
Yeah. Good. Thank you. So, guys, you are welcome to the to any Q&A. Any questions? What is that? Hello? Can you hear me, guys? Oh, Mr. Gamal here, yeah.
Okay.
Yeah. So, oh, maybe you sleep, yeah. Maybe the talk is very poor, yeah. Poor talk, yeah. Not good. Huh? Any questions? Anything? Any reaction? You like it, you don't like, it's okay, not okay. Say something, guys, yeah. You are still there?
We're here. I have a question about the tools that you use to do the
Okay.
analysis.
Yeah.
Are they built in-house, or are they some off-the-shelf tools that you can use to do this?
No, in-house, yeah. We do this one in-house, yeah. Yeah.
Okay, I saw some similarity between the last few slides you showed with the nodal classification.
Yes.
And there's a commercially available package called Paradise.
Yeah, you are right.
America,
You are right. By the way, this one from Paradise, yes, you are right. But I'm just think that, you know, yes, this one from Paradise. Okay. This one is a product of Paradise here, and we have a license in UTP. Yeah, we have license in UTP. Yeah, we have. I think we have 5 licenses in UTP. Yeah. Yes, these are the product of Paradise. Yes, exactly right.
we've been looking at that recently. I think we've had a couple of presentations from those guys.
Yes.
And of course, you know, none of us are mathematical geniuses over here. We know seismic, but we don't know machine learning.
Yes.
And I think we've struggled a little bit to differentiate this new, relatively new methodology with conventional QI work. Have you got any comments you can make about the comparison between machine learning and more conventional QI in terms of looking
QI.
at QI?
Very good question, by the way. Yeah. Thank you for your question. Yeah. And you know, I discussed this issue so many times with Mr. Sami. Yeah. Mr. Sami, I can answer the question, but I think you are more aggressive than me to answer this question. Beautiful question. Mr. Sami, are you there? Sami Kordi?
Yes.
Yes.
Yes,
you
I'm there.
Hear the question?
Yes, I'm happy that someone is finally drawing the conclusion,
yes, right.
or drawing, sorry, the comparison between the QI and machine learning.
Yeah.
One of the things that you have to be aware of is QI is based on physics, which is very good. There's nothing wrong with that. It's totally focused on trying to honor a model that we have pre-built in our head. So we have to honor reflectivity. We have to honor the sign of the reflection and the amplitudes varying with offset. Now, in the process of coining it mathematically, you have to make serious assumptions, and some of those assumptions in QI, the AVO QI combination, is that you assume everything is horizontal, and you assume that the Earth is isotropic and homogeneous. And all of these assumptions are built into the QI. Now, you have the ability to do anisotropy in QI, but usually in the practical terms, they don't apply it. So the product you get is not quite optimized when you try to figure out the subsurface characterization. On the other hand, and there's another issue which relates to the stationarity of the wavelet. That's not taken into account. You just extract wavelets at different spatial locations based on well placement, and you just blend them all into a composite wavelet, let alone the stationarity vertically, the temporal stationarity, which is well, shallow, medium, deep. Well, we have to extract one wavelet and we also blend them and come up with one. And that's what we apply. That's why it's preferred with QI to go through a specific window over a reservoir. I can't give you the full section from zero all the way to the bottom. Take that to the other end, where machine learning is totally modifiable and accepting to both non-stationarity and non-linearity.
Yeah.
So geology and waveform propagation are both non-stationary and non-linear.
Yes.
So by applying machine learning, you depending on the techniques, you can honor both of those all lumped in, and you're not tied in to this straitjacket of wavelet extraction. You're just taking the seismic as it is. This is how the seismic represents the subsurface. Whether the wavelet changes or not, I'm going to build the model accordingly at different locations, both spatially and temporally, horizontally and vertically. And this is where machine learning shines. If you tweak your model properly and have enough data to build a robust model, I have seen examples where machine learning gives a way better product than QI, because, and the QI, it's because of the assumptions they make. It's not sort of like, in the technique. It's just because they have to get the job done and they have to make these assumptions. I hope I answered the question.
I think it's very, yeah. We answered the question, Mr. Bob.
Yeah, you have. Whether I understand it fully is a whole different question, but yeah, you have. Thank you. The reason I asked that question is because there's fundamentally, it has been difficult to use QI to identify fluid
Yes.
phase in carbonates, and of course Malaysia has very important plays in the carbonates.
Yes.
And we are toying with the idea of whether machine learning would have greater success in identifying gas within carbonate porosity. I haven't seen any studies on this yet.
Yeah.
But I have high hopes that it might be able to.
Good question, by the way. But I believe that we can do it. It can be done, by the way. I know because you are from Mubadala, you have the carbonate fields. Yeah, I was, there to review some work there. Yeah, I think Mr. Sami, it can be done, by the way.
Yes,
in carbonate, gas carbonate.
It is data
very good
driven,
question.
though.
Very good question.
It is data driven. So
exactly.
it is doable, provided you have enough data. So in essence, in QI, you assume even if I have one well, I can still build a model. You cannot do this in machine learning.
Yes.
So I cannot build a model based on an idea that I conceive in my head. It is data driven. I guess Dr. Saadani has made that message loud and clear. It is data driven. What we mean by data driven, give me data, I can build you a robust model.
Yes.
Not enough data. That means if I'm not exposed to all the spectrum of available data availability, then obviously it's not going to build a robust model. So to the point of your task, yes, it can be done. And in carbonates, there is no distinction, provided you have examples of what you want to look for. So you cannot go looking for something that you haven't encountered before. If you have at least an example, then then we can train a model to look for it.
Yes.
But we cannot tell the model, look for something that I haven't given you data to learn from.
Yeah. Mr. Bob, very good, by the way. Please, you can please they send your email, because we can talk about this one. Very interesting, because in the Mr. Sami already is a consultant in Asthma Geosolution, and why not if we just have a look and and see that what we can do. I think by supervised one we can do a lot. I believe. So about the publications in carbonate, I'm not quite sure. Mr. Sam, did you see any publications in carbonate from the Gulf, whatever, using machine learning for this? Because the carbonate is a different animal.
No, people shy away. Let me just make one point clear. Even the example that was presented in this paper by Mr. Ismail, the concept is, how would you want to think about your data?
Yes.
You want to think about it as a classification or a regression.
Yes.
So if you want to break down your data into classification, meaning either binary, like yes or no, as the example, salt or no salt, or good porosity or bad porosity, or something like that, that reduces your task considerably, because then you will have more latitude for errors and you can actually broadly talk about the data. My preferred approach is to go in and do it as a regression. Frame the problem as a regression, meaning if you have a porosity log, we need to be able to predict from the seismic a porosity at every single trace, a porosity log, a pseudo porosity log, as opposed to high porosity, low porosity, which is I will assume a certain cutoff, 10% or 3% or whatever, and then and the classes in between. That gives me more latitude for manipulating the data, but it doesn't give you the fine comb with which you need to go through your seismic. Whereas if you do it with as a regression, it's more work. It involves more attributes to extract, but it's more fruitful, if that's the right word.
Yes, good, good, great, great. Is it okay, Mr. Bob?
Yes, I understand. One of the examples shown used principal component analysis to reduce the complexity, but I know that the Paradise system doesn't do that. In fact, it increases the complexity by subsampling the seismic into a much higher resolution set of bins. So it vastly increases the size of the seismic cube many times, many-fold, because it subsamples it. And it also uses a very large number of attributes, and I don't believe it uses principal component to simplify that data. So, that was an interesting thing.
Yeah.
I hadn't seen PCA.
In this case, by the way, in this case, they presented, they mentioned that they use a PCA. They said that, you know.
Is that right? Okay. Well, that obviously went over my head because I was under the impression that they were both subsampling the seismic cube to make it a much higher resolution, probably an order of magnitude higher resolution than seismic itself. And then they were correlating that with well logs. And because well logs are very high resolution, they're subsampled on a
exactly
15 centimeter.
Yeah.
Then they could do that.
Yeah. Can I make a comment? Sorry.
Yeah. Go ahead.
Yes. Okay. We're talking about two different things, sir. The first one, what Dr. Saadani is talking about is when you have many attributes, each attribute is considered as a dimension. Okay. So PCA is designed, let's say, as the example by Mr. Ismail, the 31 attributes were reduced to 2. That's a big savings in terms of building a model. It gives you more flexibility. Now, that is different from what you're alluding to of sampling, whether it's spatial sampling or spatial or temporal, meaning like increasing the number of samples. So sampling has nothing, they increase the resolution by doing the subsampling. As a matter of fact, QI, the stochastic inversion, is actually, they deliver you products at down to 1 millisecond by doing this subsampling. It has nothing to do with PCA. We're not reducing here the dimensionality. We're increasing the resolution temporally. Now, if you go in and you have a grid and you have a spacing of 12.5 trace spacing and you want to increase your spacing to 6.25, well, that's fine. That's increasing your spatial resolution if you have the ability to interpolate intelligently. That is different from PCA. PCA takes the dimension of the attributes that go into building the model. Whereas you're talking about, I have created a container that I will be predicting from. That container has a spatial dimension, meaning delta X, delta Y, and a temporal dimension, meaning the delta T, or what you're working in time, the sampling interval. So you can go as low as 1 millisecond sampling if your data is 2. That's increasing the vertical resolution, but it has nothing to do with what PCA does. PCA looks at the dimensions of the attributes that goes into building the model. I hope I'm not confusing you.
No, that's very clear. And that was my
thank you.
My lack of appreciation of how this technique really works, I guess. But we're all here to learn. So Excellent
Oh,
answer.
okay.
Thank you.
You're welcome.
Thank you, Bob. Thank you very much, Bob, for your your question. By the way, very interesting. This one coming from industry, from the kitchen. So, guys, any question, guys? Any question? I didn't see any feedback here. Yeah, in the chatting, is there any feedback form? Yeah, you like it? You don't like? Okay. Good, bad. What is that? Anything? Anything? Hello, guys. Any question, guys? It's okay. You keep silence.
Yes, Doctor. Yeah, so the feedback forms, you can find it in the chat box, as Miss Boyi just shared just now. So you
Abu,
may...
can you please, guys, can you please fill the form? Yeah, fill the form. Just we need to know, yeah, because next time, maybe if the next time or not, we can also. But I'd like to hear from you. Say something. Yeah, is it okay or not? Yeah, I don't know why you keep silence like that, guys. Anything? Anything you like to say? Anything? Yeah. This is not expected. This is good. It not is very hard. I'm talking very quickly. The conclusion is not as you expected. The coverage of the topic cover is okay or not? Can we say something? Thank you very much. Yeah.
Thank you, Doctor, for your presentation. It was quite interesting. Actually, you covered a lot of things in this presentation, like starting from the basic machine learning concepts to the geophysics insight, and so it was quite helpful, and in my opinion. Thank you again for your presentation.
Thank you, Tawheed. Thank you. This is by intention, by the way. I add a lot in the beginning because this one is your input. You have to understand it.
Yeah,
you have to understand our challenge, our problem. Yeah. We have so many problems.
I joined a little bit late. Yeah.
Yes. So
I joined a little bit late because I was donating blood.
Until now, even by the way, if I ask question now, this one, the fault connection, the fault, the fault, the fault termination here, can the machine learning can help to solve this problem? We don't know. The question always asking here, can we apply the model? Can we apply the model in ANSI to, as example, in GenCa and the MODA? Different fields, generalize. This one question, before you ask this question, can we apply your model in your area, but reprocess data? The same data, but to reprocessing with a new acquisition. Not the data changed, then the model changed. So at the end is a tool. It's a tool. We have to integrate without integration we will drill and dry holes again. Dry holes. I remember when we Mr. Sami also remember this one when the QI Sami the AVO and DHI and all this one, they put it in the poster in shell poster and the colors and like that, and we drill so many wells, dry holes, because we have pitfalls in DHI and the QI.
One thing I liked from one thing I liked from I think Dr. Sami or Dr. Bob, he was saying he was saying that we need to have like enough amount of data to train, then only we can say confidently that our model is okay, because as far as we are saying that the models are doing good, right? So but sometimes like we don't have, let's say if we're not exposed to all type of training data, like from different fields, then we cannot say that this is a general solution for this problem, because there might be another type of unseen data that might, when we're predicting that unseen data, that might be like different, because we never saw this. I mean, we couldn't train the similar type of data. So end of the day, we need data. I mean, we need to train nicely. Then we can only confidently say that our model can be a general solution to this problem. So
Yes.
yeah, this is also
Yes,
my
yeah.
observation.
Good. Yeah. I, by the way, they still also, you know, the people say that the data or algorithm, which was in most important data. Data, yeah,
I think so. Yeah.
I can put, by the way, there is the a force called the force Norwegian, you know, platform. There is a presentation there. The guy presented a machine learning, and he said that people can be cheating here. You can cheat here. Sorry for that. This one, he put it, you know, in a conference here. So you can change, not you can't. Some people that do that to twist the data to fit with the model is cheating. So and we know model is wrong. Is always we need to update. You know, they are working in industry so many years. It's like that. When once we add another point of data, so you have to look. You need to update or not. Until now, also some models is not, you know, is not, we cannot say wrong, is not complete yet. The model is not complete yet. We need to complete it yet. So we have, you know, pre-stack depth migration, data, yeah. Good. The processing people always good. Yeah, with drill wells and also uncertainty there, yeah. It's deeper or shallower than the data. It means that we have to update. Always update, iteration, update. Modeling is like that. Modeling, this is the beauty of science. This is the beautiful, not problem. If you like problems, this problem, it awaken your interest. As you know, you have to have this curiosity. Guys, anything, guys? Anything more? We have here, yeah, Mr. Ismail. We have experienced people like Mr. Bob from Mubadala, and we have also Mr. Sami. Any questions, guys? Anything need to add? Fatin, I think we finished Fatin now, yeah. I don't know where is the guys, yeah, already gone. Yeah. Okay, Fatin, anything? Please, yeah, please also send me the form, Fatin, yeah, please, yeah, okay? Okay, thank you very much, yeah. Can we have a picture or photo like that or not?
Yeah, sure, we can have the picture.
If guys, if you can open your camera, please, yeah. It was a good session, yeah. Thank you very much, yeah. Mr. Bob here, how are you?
I'm good, thank you. Yeah. Very interesting talk.
Yeah,
I would love to expand the conversation into autonomous driving, but I don't think we have time for that. Yeah, but a lot of this very relevant, relevant. And I feel that people right now who are prepared to jump into a Tesla and rely upon it to get them from A to B are in Donald Rumsfeld's full corner of the matrix. They don't know what they don't know. Yeah. I would never, within the next 10 or 15 years, ever get into an autonomous car, because it is impossible that is ever going to be a technology that works, because there are too many unknowns. And unless you neural network all of those unknowns into a single system, and then the car accesses that in real time, is never going to be able to get into a situation and get itself out of an unknown. It won't. It'll crash and it will kill you. And
you see, Mr. Sami?
That is just the way it is. That is absolutely the way it is.
Very interesting topic. Yes, right.
And I think a lot of people have faith that this technology will solve it. It won't, because there are too many variables, even for the world's largest computer and fastest computer. Maybe when 5G comes along, or 6G, right. Maybe.
Yeah, they're talking about 6G now.
Yeah.
Internet of Bodies.
Well, the problem with 6G, of course, is that it has a very short transmission distance. So you would have to have very, very short distance between your transmitters all the way along highways, and you certainly wouldn't have them off the highways. So again, maybe you could communicate with a super fast, very large database using 6G, but it's still not going to solve the problem of transmitting that data to the vehicle in a remote location. So I don't see autonomous vehicles ever really happening.
We can, by the way, if you can drop your email or whatever, we can discuss it here. Mr. Anwar, Mr. Anura, you are from? Mr. Anura?
I'm from Shari Galihes.
Shari Galihes. Oh, yes. Good, yeah. because you know when I was in the last position in Petronas, was the principle of reservoir geophysics. Yeah, so I go to Sharigali Hess, Mubadala, like that to have a discussion. You know, this one in 2015, 2016, 2014, 17, in these years.
Yes.
Yeah, welcome.
Yes,
Thank you very much for your coming.
Yeah,
Yeah, thank you. Thanks a lot. Yeah,
Thank you.
yeah, thank you guys. Yeah, so we have also so many here. Yeah, MashaAllah, Muhammad, Rayhan, and Warda. How are you, Warda? Yeah. Nur Azlina and Fatin here, yeah, of course. Yeah, Fatin, she's doing PhD with me. Yeah. Siti and my Sarah, Islam, Mr. Tawheed. Yeah. Okay, can we have go to the
Yes, okay.
okay, go ahead, Nur, Fatin.
All right, so I'm going to take a shot now. All right, so 1, 2, smile. Okay.
Thank you. Thank you. Sami,
All right.
Mr. Sami, thank you very much, Mr. Sami, yeah, for your
You're
timing.
most
Yeah.
welcome.
Thank
You're
you a
most
lot.
welcome.
Yeah. Allah yabarak fik. Yeah.
Thank you.
Mr. Sami is my teacher in in machine learning. You know, geostatistics. You know, we work together, and you know, very fruitful. Yeah. And thank you, Mr. Bob. Thank you all. Thank you, Mr. Anura, and thank you all.